So, Kostya. So, Kostya, maybe it's time to start?
Yeah, it's time to start. Stefan, if you are ready.
Okay. All right. So yeah, thanks very much for the invitation. So I'm going to talk about the diagonal of 45 folds joined with Neb Pavic. And okay, so let me start with a definition. So throughout X will be a variety over a field K. And I'll be interested in retract rationality. So X is retract rational if and only if there are rational maps F and G that fit into the following diagram. So you regard the identity on X as a rational map, and then as a rational map, this should factor through projective space, like this. So F and G are rational maps, and N is an arbitrary integer, but since the composition is the identity, it's dominant. So N has to be at least a dimension of X. And a simple example, so when does this happen? So if you multiply X with some other variety, and if this is rational, then X is retract rational. And why is that? Well, if this thing here is rational, it's birational to Pn. Everything in this diagram are rational maps, so you can replace Pn by this X times Y, and then F is the inclusion of a factor and G is the projection. So in particular, if here Y can be taken to be a projective space, then one says that X is stably rational. And so in particular, stably rationality implies this retract rationality. So rationality implies stable rationality implies retract rationality. And this implies unirationality, simply because this map here has to be dominant. So there is dominant map from Pn. And right, so here the opposite is not true. And this is also not true. And here we don't know. Okay, so this is this famous example of a threefold that is stably rational, but not rational due to Coulomb, Bouville, Son-Suk, and Dyer. And this is the Artin-Mumford example. Okay, so one class of varieties where one can try to see where in this list of implications the variety sits are hypersurfaces. And so I quickly say over C of degree D, and let's assume that it's very general. All right, and then there are some classical results on this, maybe to spend. Most of you know this very well. So yeah, so cubic threefolds are not rational by Clemens-Griffith, and then quartics of D is 4 and N is 3. This has been done by Iskowski-Manin. They proved that these hypersurfaces are not rational. And then Colliot-Tilene and Perutka much later proved that they are not stably rational. In fact, not retract rational. And then still degree 4, but now dimension 4 has been done by Totaro. And again, he can prove that they are not retract rational. And Totaro has a linear bound that improves the linear bound of color, and an improvement of this due to myself that says that if D is bigger or equal than the log 2 of the dimension of n plus 2, the dimension is at least 3, then X is not retract rational. All right, so what happens if one puts n equals 5 here in this formula, then one gets D bigger or equal 5. And the motivation for the talk that I give today is a theorem of Nikkei and Autumn, who can improve this bound here. So they show that if X in P6 over C is a very general quartic, then X is not stably rational. Okay, and the point here is that these previous approaches, they all detected, in fact, not only stable rationality, but retract rationality. And so far, nobody really cared, because all these approaches that would detect stable rationality, in fact, detected this one. But there's a new approach that does, in fact, not detect retract rationality, but really only stable rationality. And Nikkei and Autumn use that approach. So they cannot, with their approach, they cannot get retract rationality. And since there is this approach that really is sensible to this stable rationality, it is a possibility that one can use that approach to prove that, well, to answer this question, to find something that is retract rational but not stably rational. So this is the motivation of this talk, and more concretely, we ask whether this quartic is retract rational or not. Well, that's one motivation. Another motivation is, so remark, so their approach does not work for retract rationality or in positive characteristic. So another motivation is to see whether one can get this over other fields, over positive characteristic fields. Okay, so before I explain the answer that we found with NAP, I want to recall how Nikkei and Autumn proved the theorem. I already mentioned that they are using an obstruction that is really sensible to stable rationality and not retract rationality. And this is the motivic obstruction of Nikkei, Schindler, and Kontsevich-Jinkel. So let me briefly remind you what that said. So if X, say, over the power series ring in one variable over C is strictly semi-stable, that means the total space is regular and the special fiber is a normal crossing divisor. So locally looks like the intersection of hyperplanes. And all the components are smooth. So if you have such a nice degeneration with special fiber, Y that has some components, then the geometric generic fiber, if that is stably rational, then there's a certain identity. A certain identity holds in the free abelian group of stable birational equivalence classes. where this one here is the intersection. So for a subset of the index, so big I is is the index set of the components, and for any subset you can intersect the corresponding components, you get some strata, and we sum up these strata with some coefficients, and this has to be the same in the free abelian group of stable birational equivalents. Let's select a point if the geometric generic fiber was stably rational. So if you find some semi-stable degeneration of your variety you're interested in that does not satisfy this equation in this very simple ring, then the generic fiber was not stably rational. But it does not follow. So this uses big factorization. So resolution of singularities very heavily. So it doesn't at the moment not work in positive characteristic, though we expect it should if resolution of singularities holds. And more importantly, the method cannot or does not work for retract rationality. So it's really special for stable rationality. And now let me recall what Nikkei and Otem do is they just write down a semi-stable degeneration of quartics where this equality is not satisfied, and then they're done. So let me prove. Proof of the Nikkei-Otem theorem. Well, you have to find a nice degeneration, and the one they use is the following. So it's given by two equations in a weighted projective space. Over this power series ring. It's a weighted projective space. There are 7 variables that have weight 1. So this is set 0 to set 6. And then there's one variable of weight 2. This is the W. And F is a quartic equation. So F is a quartic, homogeneous quartic polynomial that is very general, subject to invariance. Sorry.
And what is T?
Sorry. What is what?
What is T?
Yeah, so T is an element in this ring.
Ah, so it's the deformation parameter, right?
Exactly. Yes.
Okay.
So everything happens over this space ring, and for T equals 0, we get the special fiber, and if T is invertible, we get the generic fiber. And they assume that this quartic is symmetric in set 5 and set 6, but sufficiently general otherwise. Yeah, so there are variants of this. So you can write several variants. I use this one, and then I explain what happens. So the special fiber, I always call the special fiber by Y. What do we get? So T is 0. So we get set 5, set 6, sorry, the product. So this is a union of two hyperplanes, and then the second equation is a double cover like this. So this will be a union Y1, union Y2, where this Yi is a 2-to-1 cover of P. 5 branched at the quartic F, where, well, set 5 or set 6 is 0, but the symmetry by set 5 and set 6 tell me that it's always branched at the same thing. So set 1, Y1 and Y2 are isomorphic to each other. And Y1 intersected with Y2 will just be given by set 5 equals set 6, and this other thing. So if I call this set, then set is a 2-to-1 cover of P4 branched at the degree 4 equation that is given when we set Z5 and Z6. Sorry. So. Okay, so what about the generic fiber? Well, the generic fiber, we can invert T. So W will be, we can solve here for W, and W will just be this expression. And if we plug it in here, we get that it's just a quartic in P6.
T to the power -2, right?
Probably, yes. Exactly. Okay, so this is an interesting degeneration. So the generic fiber is a hypersurface, and the special fiber, maybe I emphasize this. So the special fiber has two components, Y1 and Y2, and the intersection set is this 2-to-1 cover of P4.
And is the general fiber smooth?
The general fiber is smooth, and the total space is not regular, but you need to blow up a little bit. So this has very mild singularities, and I neglect this here. So if you blow, you can do a small resolution of the total space, and that does not change the components or their birational type. So it does not introduce new components. But you see here, this equation here has well, yeah. One can check that this has some very mild singularities that one should resolve. But there are small resolutions of these things, and I neglect them here. But the generic fiber, yes, this is smooth because F was just a polynomial in Z1 to Z6 up to the symmetry. It's completely general. So if I add this monomial to it or subtract it, it's still a very general polynomial, symmetric in Z5 and Z6, and this gives a very general hypersurface of degree 4 in P6 up to the symmetry in Z5 and Z6. Okay, so why do they insist on this on the symmetry? So we need to check the following thing. So the formula says that the sum of the components minus the intersection, we need to check if this is the same as the class of a point in this free abelian group of stable birational equivalence classes. But now this is not the class of a point. So this set is not stable birational by work of Hasid, Perutka, and Schinkel. That's the key point. So this is not a point, but these two things, they are the same. So I can write, because they are isomorphic, so this is 2 times Y1. But we are in a free abelian group, and then this cannot happen. So one way of seeing this is that we can reduce modulo 2. Then we are in a vector space over F2, and in this vector space, this goes away, and we would get that the class of set is the same as the class of a point, but it's not true by Hasid, Perutka, Schinkel, so this is not true. And this proves the Nikkei theorem.
So you need to, so you first reduce and then apply Hasid, Perutka, Schinkel, right?
No, so I need to prove that this does not hold.
Yeah.
And one way of, so what you mean with reduce mod 2 or?
Yeah, so do you use something like Hasid, Perutka, Schinkel over
No. So this is
just an argument about a free abelian group.
Absolutely. yeah. So this is a very stupid argument. Just in such a free abelian group, there's no way that you can find a class y1. So there's 2 times y1 minus z would be the class of a point, because z is not the class of a point. And one way of seeing this is that if such an identity would be true, I can tensor everything with z mod 2, just in this free abelian group, and this would go away. And then I would see that in the free abelian group over z mod 2 that is generated by stable birational equivalence classes, the class of z would be the class of a point. But that means that they are the same because it's a free abelian group or a vector space, right, over Z2. Is that convincing?
Yeah, I think possibly it's fine. Yeah.
Yes. So that they have the symmetry to get rid of this. There is another argument. So alternatively, we can make y1 and y2 singular. In fact, put a triple point there, and then they are rational. So okay, so this technically speaking, this makes more trouble, because then one has to, in the semi-stable reduction, one has to blow up the triple point and so on. So I don't want to show this here, but one can do that, and the new components that you introduced, they don't really mess up. In any case, so what I want to say is that one can get into such a situation where the two components are in fact rational, and then it would even be easier to see that this does not happen, because then this is the class of a point, that's the class of a point. You can cross out one point and you would get that this class is the class of a point. Okay, so the question is, the first question, if we have a quartic in P6, is it retract rational? Okay, and if it is, then it's probably, at least for me, impossible to find such a factorization of the identities. The only hope is that maybe it's not, and then we can prove that. But if we want to prove that, then the second question comes up is how to replace the motivic obstruction of Nikkei, Schindler, and Koncevich-Zinkel in the above argument. I mean, this result of Koncevich-Zinkel and of Nikkei, Schindler, Koncevich-Zinkel is very, very central here, and one needs a replacement for this. So what I'm saying is that I want to use the same a similar degeneration. So I want to use a similar degeneration as they are using. So one has two components, and this intersection is stably, or it has no decomposition of the diagonal. It is non-retract rational by work of Hasid-Perutka-Zinkel. So I want to use such a degeneration, but then I would like to conclude, or like to see whether this implies something about the generic fiber. And the known methods that we have for this problem don't work. So one has to do something new here.
Yes, Stefan, and so what does the argument of Nikkei Sotom prove? So apparently they prove that like a 5-dimensional quartic is not stably rational, but does it also prove higher dimensions by induction?
No. What
happens if we apply it to a 6-dimensional quartic?
Yes, then you would need to know that double covers of P5 branched along a quartic are stably irrational, and we don't know.
Branched in a 5-dimensional quartic, right?
Yes. sorry, yeah. So roughly speaking, what Nikkei said, so this is a very nice and super clever degeneration. And what they managed to do is they managed to squeeze out more from the Sasset-Perutka-Jinkel example, because that example, you know, in dimension 4, we have this totaric result that quartic fourfolds are not rational. Mm-hmm. But the Sasset-Perutka result is much better because it says that double cover, well, it's better because double covers of P4 branched along a quartic, they are somehow closer to being rational.
I see. So yeah, I see.
Yeah. So there is no way of
a bigger index, right?
No, the index is the same, I think.
No, Fun index is bigger for the double covering.
Fun index is the same. This generation of one the same. In dimension 3, both have index 1, for instance.
No, in dimension 3, quartic.
Oh, sorry. I'm totally confused. Which double cover is this? It's a double cover of projective space branched in a quartic, right?
Yes.
Yeah. Yes. Sorry, the index is bigger. Yeah.
I mean, the way I think about this is that it's an equation of this form, and this is a very special degree 4 equation, right? So if you dehomogenize it, it's just a special degree 4 equation. So this is, yeah. And in higher dimensions, to do an inductive argument, you would need to prove something for these special equations, and not for a general quartic. So there is no inductive way that one could go on, at least not an obvious one. Okay, so
and maybe
yes.
just one last question.
Yeah.
So Sasset-Perutka-Jinkel, they also need some generality condition anyway, right?
Right.
But
right, that is all fine. So in this construction, F was very general. Only there was not only the symmetry condition, but for instance, you have no condition whatsoever. What happens if you put Z5 and Z6 being 0? So this restriction is really a general quartic equation. So this is a very general 2-to-1 cover of P4 branched at a very general quartic degree 4 equation. Yeah. Okay, maybe one more thing that one should say is that Nikkei and Autumn don't only have this very nice degeneration, but they also have a conceptual way of thinking of them in terms of tropical geometry, and that's how they can do complete intersections in large dimensions. And that's a conceptual way how you get these degenerations. In low dimensions, you can just write them down, but the larger dimensional examples they have, you can't easily write them down. However, for hypersurfaces, this is the only new example, and there we can do things by hand. Okay, so back to my question. I want to use a degeneration like this, or maybe a similar one, and want to see whether this does obstruct retract rationality. And for this, I need some kind of replacement of this Nikkei-Schreider Quantization result. And so right. So let me start out very simple. So how do we obstruct retract rationality? And this, in fact, also explains why this is a very natural notion. If you see it for the first time, you might think this is strange, but it's very natural. So assume that you have a functor from smooth projective K varieties to abelian groups, which is functorial for rational maps. So either contravariant or covariantly functorial for rational maps. One of the two, doesn't matter. Then we have the following lemma. If X is retract rational and this functor evaluated on projective space is 0 for all n, then f of X is also 0. So any functor that is functorial for rational maps and trivial on projective space gives an obstruction for a variety to be retract rational. And the proof is obvious. So we have this diagram. And then we apply the functor. And since we assume that the functor is functorial for rational maps, we get that the identity factors through this one. And so the identity factors through 0, because I also assumed that the functor is trivial on Pn. And so that group must be the trivial group. So this is certainly the motivation for, or one motivation for the notion of being retract rational, that it's a very natural source where such functors can be used to detect it. So what are examples? So the first example is you can just take differential forms of positive degree, so that certainly vanishes on Pn, and it is functorial for rational maps, because if you have a rational map, you get pullbacks, so it's contravariantly functorial, you get pullbacks on rational forms. So unramified cohomology would also be an example, but I don't want to talk about this today. Another example is the Chow group of 0 cycles, and this is because on a smooth projective variety, you can move them all, the 0 cycles always in general position. And if they are in general position, then you can pull them back with a rational map, because you can assume that they are supported where the map is actually defined. Now, the group of 0 cycles, so it is functorial for rational.
Sorry, probably you
yes.
need to push forward, because the pullback of a 0 cycle is not a 0 cycle, right? The dimension.
I'm sorry. Yes. But what I meant, yes. But what I meant is, so you need to move the point so that the map is defined. Yes. And then you can push it forward. Absolutely. Yes. So here it's contravariant. And here it's covariant. But now this example, it is functorial, but it does not satisfy this one, obviously. So we can easily get rid of this by just looking at the kernel of the degree map. Then now this invariant also satisfies this condition. And the third example is the observation that whenever we have a field extension, then we get a new functor just by applying the old one to the base change. For instance, the kernel of the degree map. Okay, and so this so what turns out is that for smooth projective varieties.
Sorry.
Yes.
So your functor f should be then defined on varieties over L?
No, over K.
So
yes. This one, yes, that's right. Yes. The f is, for instance, this one. Yeah.
Yeah. So you extend scalars and then restrict them back. Right? So here, XL, do you consider it as a K variety?
Well, it doesn't matter really, but no, I think as an L variety, but for these, it only depends on the scheme structure, not on the.
So this is not for an arbitrary functor, but for the functor from example 2. Yes. Okay.
But you can do, of course, if you have some functor, you can do something similar. I think what you said is absolutely right. So you need a functor for varieties over L, and then you can do this business. But these examples, they are well behaved and they're doing extension of scalars.
Okay.
Okay, so if you like, I can replace this. I can remove it. So just this. I mean, we could do the same thing for the first example. but we wouldn't get anything interesting because the space of forms doesn't change. But this kernel can change. That's why this is really interesting. Okay, and so this observation leads to definitions that you probably all have heard before. So the first one is that X is universally CH not trivial, essentially if this third example is always 0 on X. And it's slightly stronger, so if the degree map is an isomorphism for all field extensions. And another definition is that there is a decomposition of the diagonal of X if there is a 0 cycle on X such that the 0 cycle of the diagonal is the same as the base change of Z. This is now this happens in the base change of X to the function field. And here, this is the class of the diagonal. So I draw a picture. We have X times X, the projection down to X. And here's the generic point and the generic fiber. And on X times X, there are two cycles. So there's a diagonal and a section given by Z times X. And now this diagonal class is this cycle. And this class is that cycle. And the decomposition of the diagonal exists if these two 0 cycles are the same. And okay, so that means also something about the global cycles on X times X by the localization formula. But the convenient way of stating is like this. And if I state it like that, then you also see that if something is universally CH not trivial, then that must be true if X is smooth projective, because this cycle has degree 1 and that cycle has also degree 1. They have both the same degree. And so the difference must be 0 if the variety is CH not universally trivial. So this is really a special case where one finds two more or less canonical cycles of degree 1 that have to be 0 if this universally trivial condition here is satisfied. And then there's a lemma that says that in fact, if X is smooth projective, then the two notions are in fact equivalent.
But how do you know that X has a 0 cycle of degree 1?
Yes. I need to assume this, yes. Okay, so now let me think. No, so well, no. What do you mean? I mean here. It's contained. It's a condition. It's contained in both conditions. So here I ask that for every L over K, the degree map is an isomorphism. So there must be a 0 cycle of degree 1.
Okay.
And here I'm asking for a 0 cycle on X with this condition, but that cycle has degree 1, so
Yeah,
Z has to have degree 1. Okay, so no, yeah, sometimes I make that mistake, but I think if I formulate it like that, then I don't.
Yes.
So if X is smooth projective, then the two notions are the same. X is universally CH not trivial if and only if there's a decomposition of the diagonal. It's more like a remark that, yeah. But that also explains somehow the title. So, but what I would like to know is whether the quartic has a decomposition of the diagonal or equivalently, whether it's universally CH not trivial. And if it is not, then this functor is not trivial on this X. And then by the lemma, X was not retract rational. Okay. So upshot of this is that if X is not universally CH not trivial or equivalently has no decomposition of the diagonal, then X is not retract rational. And yeah. So I would like to use this criterion. Okay, so now back to the Nikkei degeneration. So what's our problem? So we have a semi-stable degeneration. Special fiber has two components. The intersection is integral. And for simplicity, I want to assume that these two guys here, the two components are rational, and Z is not CH not universally trivial. So yeah, so this is okay by Hasid-Perutka-Zinkel. And I briefly mentioned before that it's more or less also okay. One can somehow reduce to the case where the components are rational. And even if they are smooth, we don't know whether they are rational or not. So let's assume they are rational and try to see what we can get from them there. So this will be somehow a simplification that I want to make now to think about the problem. Okay, so the special fiber has two rational components. The intersection is irrational. It has smaller dimensions, and Nikkei and Otem are able to use the motivic approach to deduce from this lower dimensional irrational strata the irrationality of a higher dimensional generic fiber. Now, I would like to see whether one can detect how big the group of zero cycles of the generic fiber is. So I would like to say that the group of zero cycles of X must be big if something like that happens. But now you see, if Y1 and Y2 are rational and everything happens over an algebraically closed field, then this Y, you can, after every field extension, the Chow group of zero cycles of Y is just trivial. Yes, so I can. So Y is CH not universally trivial. And so we are not happy. I don't know what to do. So the first idea is that somehow the problem is that the interesting information lies in Z, but Z is a divisor on this Y. It's codimension 1, and so it does not influence the zero cycles at all. So maybe we should blow up Z. So the first idea is 2-to-1 base change plus blow up Z, and then we get a special fiber. Well, now three components, the Y1 that we had before, and the Y2 we had before, and there's a new component, and this is a P1 bundle over Z.
Sorry, and why do we need a base change?
Otherwise, it's not strictly semi-stable. So if you blow up the yes, so if you blow up the single locus of the special fiber and don't do a base change, then the exceptional divisor will have multiplicity 2. And that's not allowed in a strictly semi-stable degeneration. So in a strictly semi-stable degeneration, the components of the special fiber all have multiplicity 1. But if you do a 2-to-1 base change, then the singular locus becomes singular of the total space. And if you resolve it, then you introduce a new component in the special fiber that has now multiplicity 1, and the total space becomes regular. So that's why the base change is necessary. Okay, so let's do a base change. Then we have three components. 2 are unchanged, so they are still rational. And this here, the middle guy is a P1 bundle over Z, but Z did not have a decomposition of the diagonal. And this is, or not, was not CH not universally trivial. And this is a stable birational invariant. And so also this P1 bundle over Z still has no decomposition of the diagonal. So this is not universally CH not trivial, or has no decomposition of the diagonal, as you want to say. Okay, so that maybe that is better, because now at least we have a whole component where zero cycles can live. But it's still not quite good enough. So here's the following example. So start with projective space over this power series ring and blow up . So let's start with the constant family over the power series ring, and then we blow up a general okay, sorry, I'm a little bit confused. Okay, so my example goes like this. So blow up a general, say, codimension 2 subvariety. Then
codimension 2 in the fiber? In
the special fiber.
Codimension in the fiber, right?
Yes, exactly. So then we get, and then followed by blow up of point on exceptional divisor. And then what we get is this. So the generic fiber will still be Pn, and it degenerates to something that has 3 components. Let's see what are the components. So one component is the blow up of Pn and Z. The other is a P, okay, I took codimension 2, so it's a P2 bundle over Z. And in fact, the blow up of this thing, because in the last step, I blew up a point on this P2 bundle. So blow up of it. And this last exceptional divisor is a Pn. And now you see we are exactly in the same situation as before. So this is rational, and the guy in the middle has no decomposition of the diagonal, but yeah. this is rational. And that one is also rational. Okay, so this is an issue. So one has to look somehow closer. So what I'm saying is that we would like to use this Nikkei Autumn degeneration, but what do we know about the degeneration? Let's assume that y1 and y2 are rational, and then all we can get is we can get such a degeneration where we have three components, and the component in the middle is not universally CH not trivial. But one has to use quite fine knowledge about this degeneration, because just the fact that there are three components ordered like that and being rational without a decomposition of the diagonal and rational is not enough, as this simple example shows. Okay, and now while writing down that example, I'm a bit puzzled about what I want to do now. Okay. Okay, so sorry that Jared, I prepared something, but I think there is an issue. So let me skip that what I prepared. I'm confused now. So let me directly go to the obstruction. Okay, the one that we use that should detect, well, an obstruction which on this special fiber is non-trivial, but is trivial on such special fiber. And in fact, it should be an obstruction for retract rationality or decomposition of the diagonal of the generic fiber. And of course, in this example, the generic fiber is just Pn. So our obstruction has to be zero on such degenerations, but we would hope for one that is non-zero on such a degeneration. Okay, no, this is already a bad start. So this is strictly semi-stable, but R is an arbitrary DVR with residue field little k algebraically closed. That's the setup. Okay, and then we look at a map. So as before, the special fiber is Y, and I denote its components by Y lower I. And what I would like to write down is a map that starts, okay, so this is incorrect. I would like to write down a map that starts with a 1 cycle on Y and spits out a 0 cycle on each component of Y. And there is an easy way of doing this. So if we have a 1 cycle on Y, this special fiber sits inside the total space. So we can push it forward, and then we have a 1 cycle on the total space. But each component of the special fiber is a Cartier divisor, so we can restrict this 1 cycle to the Cartier divisor and get a 0 cycle. So we get a map like that. So we have a 1 cycle in the special fiber, push it forward, restrict it to a component, get a 0 cycle. And now the fact that the whole special fiber has trivial normal bundle, you can move it away from the special fiber, easily implies that if you sum up the degrees of all these classes, then in fact you get 0. So in other words, this will sit actually in the kernel of the degree map to set. Okay, and now here's our result. So Pavic and myself. So first, assume that the generic fiber is universally CH not trivial or equivalently has a decomposition of the diagonal. Then for any unramified extension of discrete valuation rings. So okay, so what's an unramified extension of a discrete valuation ring? Think about the case where R is just a power series ring over C. Then for any extension of C, you just write down the new power series ring over that bigger field. So that's a typical unramified extension of DVRs. A ramified extension would be one where T goes to T squared or something like that. So example, take an extension of the take an extension of C and look at this extension. That's a typical unramified extension of DVRs. And for any such extension, we can base change the whole situation to A. And then we get a new family, now not over R, but over A. And this map still exists. And the statement is that whenever you do such a base change, that map is always surjective. So in other words, to retract rationality or a decomposition of the diagonal of X ether, it would be enough to find a special fiber so that this map here is not surjective after some base change. And the point is that this map, the way I wrote it down, it depends on the total space. But the point is that it in fact does not depend on the total space. It only depends on the special fiber. So this is really an abstraction where you only have to look at the special fiber and how the components intersect. And why is this? So this thing is easy to understand. So if gamma has support on a single white J, then we can compute this easily. So either it's just given by you intersect the one cycle with white J. If with white J intersect with yi. So white J is another component. So if I is different from J. Fi. So if you have a component, if you are at a component and the cycle has support on another component, then how do you intersect? Well, you do the obvious intersection, right? And this has only to do that, you don't need to know the total space. You only need to know the way these special fiber, the components of the special fiber meet. And now what happens if the curve, if you want to restrict the one cycle to a component that contains the one cycle, well, then it doesn't work that well. But then what you notice is that that component is rationally equivalent to the negative of all the other components. So you just intersect with all the other components. So it's something like minus gamma intersected by k, where k is different from I, if I is j.
So you just multiply by the first Chern class of the normal bundle, and it is equal to minus some of the other components, right?
Okay, that's a way of saying, yes. But then you need to know, well, no, I think that is fine, yes. As long as you agree that this is a statement only about the special fiber, that has nothing to do with the total space. So it's just a statement about the special fiber and about 1 cycles and 0 cycles on this thing. And if the generic fiber is CH not universally trivial, then the special fiber has to have the property that this funny map that I wrote down is always surjective. Okay, and then what you can do is you can write down some degeneration, look at the special fiber, and try to find a 1 cycle in here, maybe after some base change, that has degree 0, but it's not hit by that map. Now the issue here is that this only says something about the generic fiber, and we would be interested in the geometric generic fiber. So for this one has to work a little bit more. So if the geometric generic fiber is universally CH not trivial, and then I need to assume that the special fiber is a chain of components. So the dual graph is really a line. So it looks like this. So there's one component, another component, and so on. Yeah, so the simplest non-trivial case that you can imagine. And if we are in that simple case, then we can then we still get a statement on X, and we get that for every unramified extension of DVRs, this map from above applied to the base change of curly X is surjective modulo 2. Okay, so what's the point about 2? Well, in practice, if we have some nice degenerations like the one of Nikkei, we would like to apply this. Well, but I don't want to say that the generic fiber is not stably rational or has no decomposition of the diagonal, because that is a variety over a non-closed field. I want to say this over the geometric generic fiber. One way of doing this is to do a base change, but then I have no control on the base change. And after resolving the singularities, the special fiber will have a lot of components. And then it's difficult to compute this map because there will be a lot of components. In theory possible, but difficult. 2 has an advantage because if I write down one model with very few components in the special fiber, this map here is easy to compute. I have few components. Nonetheless, I can make an assertion about what happens on the geometric generic fiber. So what happens about base change. The price I have to pay is that I only get surjectivity modulo 2 and not surjectivity on the nose. However, the way we will apply the theorem, we will apply 2, and we will find a degeneration with 3 components where I think 3, yes, that is similar to the Nikkei degeneration, where after some unramified extension of DVRs, we find a 0 cycle in here that has degree 0, but cannot come from here. So that's how we prove the following theorem. So we apply 2 of the theorem to a degeneration similar to Nikkei's autumn to get the following theorem. So the characteristic of the field should not be 2, and X is a very general quartic. Then X has no decomposition of the diagonal, equivalently is not universally CH not trivial, and hence X is not retract rational. And the remark is that if the characteristic was positive, then rationality was open for these varieties. Okay, so I think I'm already over time. So let me stop with one more remark here. So there are two remarks. So yes, I don't have time to prove that theorem, but two follows from one by looking at what base changes do. So the main point is one, and one is in fact a surprisingly simple statement, but it took us quite some time to realize that such a thing exists. Well, that this is the correct thing to look at. So that one has to look at these one cycles. But it does not have a difficult proof. So the proof is quite simple. I could show it in 5 minutes. But then to apply it, this is really a lot of work, because so the Nikkei example on the nose doesn't work. So we need to look at some variant that depends on a lot of parameters, and we need to do a lot of degenerations to control the situation. And the main issue is that if you want to apply such a map, okay, so maybe you know something about CH0 of the components, and you find an interesting zero cycle here. But the problem is that you need to control it does not come from Chow1. So you need to know Chow1 of these components, and that's difficult. So computing Chow groups of varieties in general, very difficult, and in particular, Chow1. So the only way we can control this is that we include a lot of degenerations that make our components simpler and simpler, so that we can control better the Chow1. So this is a technically, unfortunately, not so nice and not so simple, but it works. Okay, I stop here. Sorry for going over time.
Thank you. Any questions?
Can you explain which degeneration do you consider? You said it's similar to Nikkei Sotem, but
it's very similar. The only problem is that you need to. So in Nikkei Sotem, well, the picture is the same. Where is this degeneration?
Yeah, it's here.
Here. Okay, so one difference is that F here was quite arbitrary, apart from some symmetry conditions. We don't care about symmetry conditions, but our F has to have certain degenerations, and yeah. So this part is technically demanding. I'm not sure I would even be able to write down the correct equation now out of the top of my head. And then also this on the nose is not the correct thing to do, because so one also has to change this one, and that's because in the whole discussion I neglected the singularities you get. So that total space is actually not strictly semi-stable. You need to blow up something, and that also causes problems. You know, these are small blowups. So a small blowup doesn't change the stable birational equivalence type of the components, but it does change the Chow1. So we need to take care of this. So it's essentially the same thing, but different. Sorry.
And
a little bit different, yeah, but very similar. So for instance, the components they should have degeneration, so that they are smooth, but they allow degenerations to something that has a triple point, so that it is rational, and you can then use a rational parametrization. You know, you realize it as a blow up of P something to compute its Chow1. That's one important step. And then yes, okay. So I think to simplify manner, we actually keep the symmetry between Z5 and Z6, even though it's not so essential. But we keep that trick from Nikkei Sotem just to simplify computation. And then there is one more technical subtlety that one has to change this equation a little bit to keep track of what you introduce by these small blowups. So so I think that's all.
But do you at least keep it quadric?
Yeah. So it's essentially that example. You just manipulate it a little bit. But,
so you increase the rank of the quadric slightly, right? Do you?
Well, where is the quadric? This one?
Yeah.
Yes, yes, I think so. Yeah.
Okay. Thank you.
So in Y,
yes. Where should I scroll? Here?
so may I ask, why was characteristic 0 crucial for Nikkei's quantum?
Yes, so that result is really, you look at the two total spaces. So you assume the generic fiber is rational. That means the total space is birational or stably birational, but you can reduce to being rational to the trivial PN family. Okay, so you have this rational map, and then you use weak factorization. You blow up, blow down, blow up, blow down.
So just to reinterpret the Grothendieck-Ring model. Yeah. So
and then you just keep track of this formula that I wrote down in each step, and you see it doesn't change. And so at the end of the day, you need to get a point because that's what you get on the right hand side.
Weak factorization is.
But so it's weak factorization is very central to this. So if you don't have resolution of singularities, that is not going to work.
Mm-hmm. And a philosophical question. So this possible example to retract rationality being different from stable rationality failed. And so what do you actually expect in this direction?
Well, I'm pretty sure that they are different. You know, all these notions are different, but it's difficult. I don't know. I mean, the problem is, okay, so for sure so my feeling would be that this motivic obstruction could in fact be sensible to stable rationality. You know, it could be the right tool to detect something that is stably rational, but not retract rational. But what I don't know how to do is how to construct an interesting variety that is retract rational. Mm-hmm. That's okay. I mean, one possibility would be a variety that becomes rational after product with something that is not projective space. But also that is it's a completely open question whether something like that can happen.
Mm-hmm. I see.
But I wouldn't be surprised if that motivic obstruction at some point will actually lead to a counterexample.
You mean becomes rational after a product with something which is itself not stably rational?
Yes, exactly.
Yeah.
But how about low dimensions? For example, surface over non-closed field. Is it maybe more clear? No?
Oh, that's a good question. I don't know if people looked at this. I haven't thought about it, so I probably can't answer out of the top of my head, but this might be feasible. I mean, it sits in between unirationality and stable rationality. So, yeah, I don't know. I would guess that one can answer it for surfaces, but I don't know.
So any more questions? Then let's thank Stefan again. It was a very nice talk. And I think we resume in 15 minutes for the last talk by Vadim Vologodsky. So see you soon. Thank you.
About quantization of symplectic varieties over the ring of integers and over other rings. The main result is due to Roman Travkin and its write-up, which is still very much in progress, is joined with Ekaterina Bogdanova, Dmitry Kubrak, and myself. Okay, so thank you very much for inviting me to speak here. So the setup is the following. So I will fix some scheme X over R equipped with a Poisson structure. So there are okay, thank you very much. Yeah, so so X is a Poisson scheme. So this is the bracket, Lie bracket on functions, which has a property that the commutator is a derivation with respect to usual multiplications on x. So a quantization. So this is Poisson structure. Quantization of this Poisson scheme is a sheaf. We work with the risky topology at this moment, a sheaf or H of algebras over my base ring R over the power series in form of variable H over this ring R algebras together with an isomorphism. So if I mod it out by this sheaf of associative, so this algebra is assumed to be associative, but not necessarily commutative. And if I mod it out by H, it comes together with an isomorphism with the structure sheaf. So such that the following conditions are satisfied. Well, first of all, ORH is flat over the ring of power series, and complete H adic complete and secondly, so now I have to explain how it's related to this Poisson structure. So let's consider the composition. So if I have an element A here, I will denote by A bar the corresponding function. And then the relation is that the condition is that for any A and B in OH, A times B minus B times A, the commutator in this associative algebra, well, it must be 0 modulo H. So because OH is flat, it's uniquely divisible by H. And the condition is that this is the Poisson bracket of A bar and B bar plus modulo H squared. Okay. So one can check that quantization of an affine variety is the same thing as quantization of the algebra of its global functions. And so here is the basic example of quantization. So we can consider for X the cotangent bundle, the total space of the cotangent bundle to some smooth variety Y. So this has a projection to Y, which I will denote by pi. And so Y over R is smooth. So then this has the cotangent bundle to any variety has even a symplectic structure. So there is an exact symplectic form d eta. It's a two-form on X. And it defines, in particular, it gives me, it's non-degenerate, so it gives me an isomorphism between the cotangent bundle to X and the tangent bundle. And if I have a differential form, df, I will denote the corresponding vector field, which is called the Hamiltonian vector field, by hf. And then the Poisson, the associated Poisson bracket is defined by the formula. So the commutator is the derivative of G with respect to this Hamiltonian vector field. Now, in this case, there is a natural quantization of this symplectic of this Poisson variety, which is given by differential operators on Y. So the differential operators is a sheaf on Y. It's a sheaf of associative algebras. It's a filtered sheaf. There is a filtration given by the order, and then can apply the Riesz construction to construct a deformation of this associative algebra to its associated graded algebra, which is the symmetric algebra of the tangent sheaf. So it works as follows. So you consider power series in differential operators with power series with coefficients in differential operators, and here you consider the subalgebra d by h, which is called asymptotic differential operators, and it is generated by functions and h times vector fields on Y. Okay, so so this is still a sheaf of algebras on Y, and it has the property that if you mod it out by H, then you get the commutative algebra, symmetric algebra of the tangent sheaf. So now, as I explained, given in the affine case, given a quantization of a variety is the same thing as given quantization of the algebra of global functions. So this general fact allows to localize dyh over X. So I will. So there is it gives rise to a quantization with the property that its sections over pullback of an open subset of Y is this algebra of asymptotic differential operators, global sections over. Okay, so in this property, you need to determine for sub H.
Excuse me. This dyh, you said it's generated by OY and HTY. Looks like the quotient is just OY.
No.
Quotient by H.
So think of the following example. Y is, say, spec maybe K of Y. Then X is spec K of X, Y, right? This cotangent bundle. And then, okay, so what is dy? It's algebra generated by two variables, by variable, global functions, global differential operators is K of X of Y dy, and the relation is that Y dy is equal to 1. So now what happens if I take dyh? Well, that's going to be algebra generated by two variables, y and dyh, and the relation is going to be that the commutator, so this is 1, and here the commutator is going to be h, right? Yes, so and I need to add formal. So
yeah, then the quotient is just by h looks like to be just k of y, right?
No, because h times dy is not divisible by h in this ring.
It's just notation. Okay.
Okay, does it make sense?
Looks like
it's not a notation; it's a subalgebra here. But I take...
And why do you put double brackets? It seems that this subalgebra is just generated in single brackets over h.
Yes, I could define it over just polynomials in h.
I mean, it is contained there, right?
Yeah. Well, no. All polynomial power series in h. In fact, if you want to localize it over the cotangent bundle, then you really need the power series in h.
So I mean, when you say generated by OY and HY, you mean also H completion?
Symbols, right? So it has two generators.
Yes.
H, Y, this symbol H dy, and subject to this relation.
I see. It is K of H. Right. K. It is a subalgebra over Taylor series.
Right.
I mean, in the general definition of dyh, you meant the subalgebra over Taylor series. I got it. So,
yes.
Yeah.
So that's what I wrote here.
Generated over K of H.
Maybe misunderstanding was that quotient by H means quotient by H multiplied by dyh, right?
Right. Thank you very much. Okay. Now it makes sense. So that's called the risk construction. All I use here is the filtration on the algebra of differential operators. Okay. So so this way I get a canonical, well, very say canonical quantization of the cotangent bundle to any smooth variety. And in fact, there is even more canonical quantization of the same variety, the same Poisson structure. So you can sort of first generalize this. Well, let me put it not generalization, but a variant of this construction. Okay, so instead of differential operators from functions to functions, you can consider differential operators from a line bundle to itself, which is also form an algebra. So differential operators on y, and for the line bundle, I want to take their canonical line bundle, right? So I can consider differential operators from sections of K to sections of K. So, so of course, you can generalize it now even further. You can replace this this line bundle by any power of this line bundle, and in fact, even by a fractional power. In fact, you can take any power which is an element of this base ring R. For example, you can consider differential operators from square root of the canonical bundle to itself. Even though it's not a vector bundle, it's not a line bundle, differential operators from this fractional power is still defined. So you can construct this algebra, for example, first by choosing local trivializations and then glue. So you first do it for integral power and then observe that the resulting algebra is defined for any fractional power as well, provided again that 1/2 is in R. Okay, so and this gives me a quantization. So again, this is a filtered algebra. I can apply the risk construction, and I will refer to this the quantization that you obtain this way by as the canonical quantization. So canonical quantization of the cotangent bundle. So it's given not by the usual differential operators, by this twisted differential operators. It has one advantage that it has is that, well, as we know, the shape of differential operators is non-commutative. So a priori, there is a difference between left modulus over this algebra and right modulus. Nevertheless, the categories are equivalent. So, and the equivalence is given by the tensor product with the canonical bundle. So if you instead consider these twisted differential operators by the square root of the canonical bundle, then so this algebra is actually isomorphic to its opposite algebra. So the functor from left modulus to right modulus is the identity on the underlying vector spaces. And so this amounts to saying that this canonical quantization has the property, the following property. If I place here h by negative h, so if I consider the same algebra with different action of h, then it's isomorphic to OH canonical opposite. Okay, that's why it's sort of better than. Okay, so this is a basic example, and now questions. So what is what we want to do now? We want to understand. Well, we want to classify quantizations of given Poisson variety, Poisson scheme. So, for example, we want to see whether such a quantization exists, and well, what is the parameter space. And so, I will list some results in this direction. First result, which is due to De Wild, Lecomte, and independently Fedosov. So this guys work in smooth manifolds, real manifolds, and in this algebraic setup that I consider the corresponding results are due to Bezrukavnikov and Kaledin. They prove the following, that if the base ring is C, and so X is symplectic, in addition, they require that certain homology of the structure sheaf vanish in degrees I equal to 1 and 2. So what they proved is that the set of isomorphism classes of quantizations of X omega and bijection with elements in de Rham homology, second de Rham homology of X well, tensored with power series. So power series with coefficients in this vector space. In particular, there is a preferred element here, 0, which corresponds to certain quantization x or x canonical or h canonical. This quantization has very nice properties. So what do I mean by saying that quantization is canonical? In particular, I mean that any automorphism of that this shape of algebras is equivariant with respect to everything that acts on this symplectic variety. So it's equivariant with respect to automorphism, symplectic automorphism of x and omega, right? So, for example, if my symplectic variety is the cotangent bundle, so then this canonical quantization coincides with the differential operators twisted by the square root of the canonical bundle. So the construction is of this canonical quantization is pretty simple, but the fact that this algebra carries this section is highly non-trivial. And in fact, as we're going to see, once you have this section, you can immediately globalize, almost immediately globalize the picture. Well, you can, starting with a cotangent bundle, you can construct quantization of every symplectic variety. So this is one result. So it's over complex numbers. Now there is another result which is also due to Mezrukovnikov and Kledin. So K here is a field of characteristic P, and for safety, I will assume that it's perfect. Maybe that's also greater than 2. And here I will assume that the symplectic form omega is actually exact. Well, that's not the most general case where the construction works, but still you need some at least local exactness, local for the risky topology. So, and also I will assume vanishing of certain cohomology groups of the structure sheaf. So here I is 1, 2, or 3. And then again, so there is a they construct a canonical quantization, and together it's canonical in a sense that certain group, namely the group of automorphisms of symplectic variety X, with a property that phi upper star of eta minus eta. Well, it's not 0, but I require it to be exact. Right? So in particular, it means that omega is preserved under phi, but that's a stronger condition. And this group acts on this canonical quantization. Okay, so just a few words about how this construction works. Well, all these approaches. So there are many more important results on quantizations. For example, Pansevich proved that every Poisson structure on the affine space can be quantized, and there is a generalization to other Poisson varieties over the field of complex numbers. But this is kind of maybe an irrelevant for my talk. So, so what is a basic idea?
Vadim, I think that Roma is asking a question. Can you have a look at the chat?
Okay. Well, so maybe I hope yes, but maybe let's discuss. So the question is whether this group acts on the quantization itself, or on the category of modules over this quantization, or only on the category of modules over this quantization. So so I hope that I'm what I said is correct, but maybe let's discuss it maybe later. Maybe Roma is right. So so basic idea. So what you do? Let's say for concreteness, basic idea of one. Okay. So well, first you do the local case. So my x is formal spectrum of power series in 2n variables. Okay, so I really think of this as a formal completion of the cotangent bundle to the affine space. And my omega is the standard symplectic form, which I prefer to write dyi dxi. So let's call this this algebra A0, and now it has a quantization. Well, that's a special case of the construction that I explained about. Well, this cotangent bundle. So explicitly, I can take well, for OH, I can consider the following algebra, just the Weyl algebra. So it's an algebra which is kind of non-commutative power series with in well, 2n variables x1 xn, y1 yn, comma h, and let me also give a special name to this. So this is the Weyl algebra. I call it A sub h. And the relation is that the commutator of xi and yj is equal to h times the Kronecker symbol ij. Right? So that's agrees with this example. It's a cotangent bundle to A1 that we discussed earlier. So this is obviously, this is by construction, it's a quantization of this A0. And now, so locally, using the formal Darboux theorem, if you have now well, what you can try to do, you can so if you are given any symplectic variety, you can around every closed point you can pick coordinates such that in the formal neighborhood the symplectic form omega is given by this form, is the standard one. Again, this is the Darboux theorem. So you can identify the formal neighborhood of every point of the symplectic variety with this standard local module, and you can quantize it. And so now the problem is how you glue it. So in order to glue it, what you have to do, you have to kind of study what happens if you change these Darboux coordinates. So let's so you have to look at the automorphism group of this local module. So preserving this automorphism of this group of automorphism of this formal power series, preserving omega, and you have to compare it with the group of automorphism of of the quantization. Of course, there is a map from one group to the other. So if you have an automorphism of A sub H, you can reduce it mod H. It will automatically preserve the symplectic form. But and one can even show that this map is surjective. Now, if we were lucky, so this map, if this map had a splitting, if I add this arrow, then I could obviously glue this construction, right? I can glue, so basically locally define quantization by this formula, and this will not depend on the choice of Darboux coordinates, because this symplectic automorphism of the formal disk acts on this algebra. But unfortunately, this does not exist. So the idea is to study the kind of the kernel of this map, call it H, and well, so the basic idea is that so this group has a very large unipotent radical, and so if you mod it out by the unipotent radical, then the splitting exists. And so on the other hand, unipotent, you can take care of this unipotent radical by using this this assumption that higher homology, certain homology of the structure sheaf equal certain homology groups of the structure sheaf equal to 0, and so this finally allow you sort of to lift the canonical torsor on every symplectic variety under this group to a torsor under this group, which is which gives a quantization. That's kind of the basic strategy. So the main work is analyzing automorphism groups of this formal disk preserving omega and the automorphism group of the quantized local quantized structure. Okay.
May I ask you?
Yes.
What's the abstraction for this section?
Well, what do you mean? What is abstraction?
Can you say informally why there is no such lifting?
Why there is no section? I think so. In this group, you have kind of, for example, infinitesimal translations. Think of A0 as like really the functions on the formal disk. So I consider automorphisms of this formal disk. In particular, I can consider translations by infinitesimally small number, right? So that's kind of an example of a automorphism that I consider. So this has a large group of commutative group, and it turns out that if you pick, so this is a large commutative group, and you cannot lift this commutative subgroup to a commutative subgroup here. So you cannot leave them to automorphism which actually commute here. That's, I think, the if I, so maybe I, so let me see if I, no, sorry, I think what I'm saying is forget this.
That sounds strange.
Yeah, so I think this Heisenberg extension does not really, what I'm saying is not correct. Right, so, okay, so, but still I claim that this extension does not split. Again, so maybe we can discuss it later.
Right,
That's really an abstraction. But it's it's a minor abstraction in the sense that again, if I model out this group by unipotent radical, then the extension really splits by unipotent radical of each. So very good. So now, so what do I want to do? It turns out, which is kind of the maybe idea now, which is attributed to in literature to Deligne, maybe Kancevich, and other people, maybe Greenfield, and well, there is a long list, is that instead of looking at quantizations of algebras, look at quantizations of the category of quasi-coherent sheaf on X. So then, of course, if I have quantization of an algebra, I can consider the category of modules over this algebra over ORH, and this, I think of this as a quantization of this category of quasi-coherent sheaf. But not every quantization of this category comes from a quantization of algebras, and it's so it happens that quantization of categories are easier to construct. The description of these quantizations is cleaner. On the other hand, so the relation between quantizations of algebras and categories can be also understood. So the idea is to split the problem of constructing quantization of algebras in two problems. First, constructing quantization of the category, and then passing, well, constructing a generator of the quantization of the category. So in particular, so if X is affine, then, well, every quantization of the category comes from quantization of an algebra. In a sense, these are the same thing, but, well, not quite. You'll see the difference. So the difference is in autoequivalences. Okay, so let me explain what I mean by quantization of a category. So digression on, say, just abelian categories. So I need to tell you, what does it mean to deform an abelian category? Okay, so let's go back to this first slide. So when I defined the notion of quantization of an algebra, so quantization of an algebra is a sheaf of flat algebras over the power series together with an isomorphism model with of OH model H and the original. So we have to make sense of this for categories. So okay. So let's try. Let's see how it works. So suppose I have A in a abelian category. Over R. R is some commutative ring. And I will assume that my category has all direct sums and some compact generators. So then what I can do, so what does it mean that the category, abelian category over R? It means that home space in this abelian category between any two objects is an R module. For example, if my category, think of about the category of modules over some R algebra. That's a good example. So if I have such a category, R linear abelian category, then I can define, I can tensor any object of this abelian category by a module. So V is in A.
Excuse me, R is commutative here, right?
Commutative, right. And M is R module. Okay. So how I define this tensor product? Well, I will define it by universal property first. I will tell you what are morphisms from this object that's going to be a new object of A. And so morphisms from this to any W is hom over R from M to R module hom over A from V to W. Okay. Hope this makes sense. And now using this this condition that my category has arbitrary direct sums, you can construct that this functor is really representable. So this guy always exists. And again, if you the basic example, so how you prove it? You write M as the co-kernel of homomorphism of free modules. And for free modules, you just take the direct sum of several copies of V. Okay, so the proof is basically one line. Okay, and now I can, using this, I can tell you what it means for an object. So let's say V in A is flat over R if tensor this functor V tensor product over R, it's a functor from modules over R to A is exact. Okay, and that's part one. And part B, we say that A is R flat. The category is flat over R. If well, before I state you their definition, so here is a basic example. So so we know what it means for an associative algebra to be flat over R. So I want so if I have an algebra A which is flat over R, I want the category of modules over this algebra to be a flat category. So the question is whether you can characterize this in categorical terms, whether you can characterize a property of an algebra A to be flat over R just in terms of the category of modules over A. And the answer is the following. So A is R flat if A is generated by flat objects. Right? So
generated is an abelian category, yes.
Yeah. Mm-hmm. Very good.
There is some more intrinsic definition by Wendy and
so everything that I explain in our so this subsection on abelian categories is due to Wendy and van der Beek. Wendy and van der Beek, right? I should have said this. So
Wendy, I think her name is
so it's enough for my purposes, but they are kind of they work in larger generality. Okay. So and now so again so my goal is to define what it means to have a deformation of an abelian category. So now we can talk about flat categories over the power series. And the last thing that I have to tell you is what is the base change, right? How you can take a category over the power series and modify it by each. So so definition for a homomorphism of rings and a category, abelian category A over R. So define the tensor product. And again, so the correct definition should have the property that if A is a category of modules over some associative algebra over R, then this tensor product should be the category of modules over the associative algebra A tensor with R prime over R. Right. So, and you want to define it in purely categorical terms. So here is what you do. You take just the category is the category of R prime modules in A. So what it means is that you look at M in sorry, I used notation V. V in A together with a R algebra homomorphism from R to endomorphism over A of V. Okay. So that must be R linear. So very good. And finally, now we can talk about quantizations. Well, first of all, deformations, flat deformations of A. So let A be a category, flat over R, a deformation over the power series is just a collection of categories, A0 equal to A, A1, AN. So these are flat over R of truncated polynomials, Hn plus 1, flat. And the condition is that a n plus 1 modulo h n plus 1, which now makes sense. This is the tensor product is, well, so there is another piece of structure is an equivalence between this quotient and a sub n, which is linear over the appropriate truncated polynomial algebra. Okay? With this equivalence. Okay, so a fact which is proven by Vanderberg and Wendy is that
I'm sorry, Leuven is her last name.
What?
Wendy is her first name.
So
Leuven.
Yes. Fact. Let's see. Let me write it down. So then Berg and Leuven is that if deformations of the category of modules over some associative algebra A is the same thing, well, model equivalences. Is the same thing as deformations of objects of A, modulo isomorphisms. Okay, so once you have an affine variety at least up to equivalence, there is no difference between deforming, say, quasi-coherent sheaves and just the underlying sheaf of objects. However, well, it's not quite true because so this is only isomorphism classes. But for example, you may have a deformation. You have inner automorphisms of deformation that they kind of define. These are non-trivial as automorphism of your quantization, but this automorphism induce an end functor of the category of modules, which is isomorphic to the identity functor, right? So inner automorphisms do not act on the category of modules. But also, I mean, deformations of a category form not a one category, but two categories. So you have morphisms between endomorphisms. So you have, for example, center acts as endomorphism of the identity functor, and so on. So there is a kind of difference, but there is no difference when you pass to underlying sets. Okay, so now so maybe I will explain how what you do here, why this is true. So if you have a category of modules of an associative algebra, and you have a deformation AN. So you have a deformation of this category. You want to produce a deformation of the algebra. What you do, you consider A as a free module over A. So this is an object of A0. And so it's projective. It's free, and therefore it's projective. And you show that a projective object can be lifted, admits a flat lifting. Well, even a projective admits a lift to let's say M to AN under this functor. And so you define AN to be endomorphisms of this lift, and you need to take the opposite. So then if you consider modules over this guy, you recover this algebra. So the reason why deformation of the category is the same as deformation of the algebra in this case is that you have projective generator. Okay, so now what is the main result? I'm ready to state it. Main result. The result is the following. So suppose I have a ring R, and I assume that it has one half in it. So 2 is invertible. And I have a symplectic variety, X over R. And I assume that my form omega is exact. Exact. And so then the category of quasi-coherent sheaves on X has a canonical quantization. Well, what do I mean by quantization? Well, I explained for you what is a quantization of what is a deformation of a category, but what does it have to do with the Poisson structure? Well, so the fact which is due to Lowen and van der Berg is that locally every deformation comes from deformation of an algebra. So it makes sense to say that this deformation of the category is compatible with the Poisson structure. So let's say denote this quantization by Popoff X canonical. Again, the basic property of this is that it has the word canonical here, in particular, that everything that preserves this structure acts on this category. So I will tell you precisely what the group that acts here. So I consider all automorphisms pairs phi, comma s, where s is a function on x, and phi is an automorphism of x, with the following property that phi upper star of eta minus eta is not zero, but it's differential of s. Okay, so I consider all automorphisms that translate this one form by an exact form. And this group, you can easily, well, construct a group structure here, right? So you want to compose automorphisms and figure out what you need to do with these functions to make this condition satisfied. So that's a group, and it acts here. So it acts by autoequivalences. That's the main statement. And in the remaining few minutes, I want to sort of tell you what the idea of the proof is. Okay, so you as in Bezukhovnikov and Kaledin story, and well, Fedosov, so you first do it locally. So you construct, you consider local module. So you take just power series in two n variables. And here you do have a quantization, so it has a map to y, which is going to be a formal spectrum, another formal disk. It's a formal spectrum of these guys. And now, so here I have the, so my claim is that it's enough to construct a global quantization. It's enough to construct an action of group G, which is again the group of all pairs phi in automorphism of x, and s is a function such that phi upper star eta minus eta is equal to ds, and eta here is sum of xi dyi on the category of modules over the quantization. I already have this this notation a sub h, so this is a completed Weil algebra in generated by xi, yj, and the commutator is equal to h. So okay, so that's kind of the main work is here, constructing this section. And so what you do, so I will explain it. So here is what so the main idea is to look at certain elements in this group, which are called transversal. So so let's say that phi in x, its endomorphism of x, is transversal if the following condition is satisfied. So we can consider the graph of phi it's a closed subvariety of x times x, and it maps to y times y. And the condition is that this composition is an isomorphism. So this graph of phi is transversal to the fibers of this Lagrangian fibration. And so now, so for example, the identity automorphism is not transversal, but the automorphism that interchanges x, I, and y, I, is transversal. So, and well, so one can check that every automorphism is composition of transversal. So you you construct action of symplectic automorphisms which are transversal. So given phi and s.
Excuse me, is it now about power series and then variables?
Yes.
Not any affine, right?
It's more than it's yes. X is just the formal disk as well. Okay, so I think of this kind of X as a formal completion of the cotangent space to the affine line, and Y is the affine space, and Y is the completion of the affine space. It's a local, kind of very local module of everything. So and you sort of reduce everything to this local module using a version of the Darboux lemma. But again, so the main point here is constructing the action of this group G on this category. So this group G does not act on algebra itself. It acts only on the category. And so given an element, well, we want to construct its action on the category of AH module. So define its action on modules over A sub H. Well, how you define this action? So an action, well, an underfunctor of this category is given by a bimodule, right? So so we want a bimodule M phi sub s over A sub h with the property that if you mod it out this by h, then you get the bimodule corresponding to phi, which is a structure sheaf of gamma phi. And you see this gamma, the structure sheaf functions on the graph of phi. The graph of phi is identified by this projection with y times y. So in particular, functions on this graph is a free module over functions on y times y. It follows that this kind of quantization of this structure sheaf should be also a free module over functions on y tensor with power series in H. So, and this suggests that this should be easier to define this. So what you do, you just take the free module of rank 1 and you introduce an action of this value algebra, which is kind of action of the differential operators, asymptotic differential operators, by adding this symbol e to the s over h. So I recall that s is phi upper star of eta minus eta. And you take power series in each. Okay. So what do I mean here? So I need to tell you why this is a module, how H sub H.
Sorry, maybe DS, right?
No, how this acts here. So you can think of this geometrically as a D module on Y.
No, I'm asking the condition. I mean, eta is a one form, right?
Yes, thank you very much. Thank you. So so I want to construct a D module on asymptotic D module on Y times Y. And for this D module, I just take the trivial line bundle, and the connection is dictated by this function S. So what I mean here is that xi, so yi act here just by multiplying by functions, and xi act as follows. So xi multiplied by, so if you want to act by xi on f times s over h, so what you do, you differentiate this expression with respect to d over dy. So so this is by definition h d over dy I of f plus ds over dy I times f, and you multiply this by exponential of s over h. This is just a symbol. So you apply the Leibniz rule. So again, so for every, not for every, but for at least for transversal element of my group of symplectic automorphisms of X, I constructed a bimodule. So I constructed an endofunctor of my category. That's not enough. So you also have to explain why. Well, not you have to construct a isomorphism between the composition of two functors corresponding to phi and s and phi prime s prime, and the functor corresponding to the product of these elements. You have to really show that this is a group action. And but well, I think I have to stop here. Thank you very much.
Any more questions about this detailed talk?
May I ask a question? May I ask a question? Do we have still time or not?
Sure. We're not in a hurry.
So you said you define it for transversal, then you should check that the composition works okay, but you should also, I don't know, I mean, it's some generators. You have some relations between these generators, right? When you define the whole group.
Yes.
So you should check. You should know these relations, right?
No, you don't want to write down. So you argue that it's that just it suffices to given an action of this group, of the whole group, it suffices to construct an action of transversal elements and the composition data for only for transversal ones. So the composition of transversal need not be transversal. So all three must be transversal. Right. So for some other formal reasons, so it's once you have this this datum for only for transversal one, it extends to all.
You mean by formal, you mean you really use this formal argument that everything are power series in H?
Yes.
I see, okay. All right. Thank you.
Any more questions? If no, let's thank Vadim once again. And thank you for everybody who gave talks and who attended the workshop. It was nice to see you all.